Okay, so let's say that the 2-minute break is over. So we resume on the same topic with a long title right now with Jacob Shapiro this time. We'll just continue what was introduced by Michael earlier. So we are listening to you.
Thank you. Thank you so much for the invitation. And also thanks to my collaborators, Michael Eisener, which just spoke, and Ron Pellet and Matan Rael. I'm grateful that they are here, and I invite any comments if necessary. This is a great privilege to have the collaborators. So I would just, I plan to continue essentially what Michael was presenting, and go as much as I have time for. So the first result that was mentioned here was an extension of the Lemaire's delocalization proof. So essentially. So if I'm not mistaken, this was in 2020, in December. So it says that for planar graphs of degree 3, if lambda is sufficiently small, then the ZGF, actually the proof is for more general models, but let me for now stick to the ZGF, delocalizes. And as was mentioned just earlier, one way to gauge that is the divergence of the second moment of the height of at any vertex. So how we extend this result is simply to say that the second moment or the ZGF fluctuations between any 2 points n x and y for the ZGF on a graph G with coupling constant lambda are bounded from below by the fluctuations of the ZGF on another graph with another coupling constant, but between the same 2 points. And here G would be any doubly periodic G tilde is a resulting surgery operation that you can get out of G that has degree 3. And lambda tilde in this case would be some higher value than lambda. For example, we find that this is 4 lambda. So in particular, what this inequality tells you is that the delocalization on degree 3 graphs implies that on more general graphs. And so out of this, we get also that ZGF delocalizes on Z2, for example, because we can relate Z2 to a degree 3 graph. And the first thing I'd like to show you is just how we show this. And the way in which we do it is through a series of monotonicity inequalities that we did not invent, we just stumbled upon. then they are also relatively recent due to Regev, Stevens, Davidovich from 2017. So let me start by presenting this theory, which we call RSD for Regev, Stevens, Davidovich. And if I'm not mistaken, and I don't know a lot about it, but they were actually interested in these questions due to different context of computer science, but turns out that this is also very much helpful for height functions and eventually also to spin models. So let's see what is this theory at all. So in this theory, you have a lattice, which is really just a subset of Rm. Let me use the dimension m instead of n, because n was the field of the height function in the ZGF. So I have a lattice L, which is the following set of vectors. So V would be any vector in Zm, and this is for a fixed matrix L, m by m matrix. So here you pick any dimension m, and you pick any such matrix which defines your lattice, and you get this set. The simplest choice is, of course, that L is the identity matrix, and then fancy L is just Zm. But you can make other choices. So that's the first thing that you need to specify. And the second thing you need to specify is the covariance matrix. So you take some A that is also going to be m by m. And furthermore, you ask that it is positive. So this just means that it's equal to B star B for some other matrix B. Okay. And out of this, you can now define a random field. Which takes values in this lattice. So in a sense, if you want, what it is really a function from the set, the index set 1 until m, onto these sets of values. But we don't want to write it like that because of this matrix that can shift things and skew them. So anyway, so this field, one way to define it is through the partition function, which we write like so. So it's going to be the sum over all possible configurations. L, the fancy L is the configuration space, and then you put the Gaussian weight. So this is, as Michael already mentioned, this is could be a Gaussian random field with covariance matrix A, but the crucial distinction is that you're not integrating over Rm. That would just be, well, the GFF with covariance matrix A. We're not doing that. We are rather restricting the field to take values in this very general lattice fancy L. Okay, so that defines your random field, and out of this random field, the quantity of interest, what we're mostly interested in, going back to the questions that Michael was presenting, is the moment generating function for this field. So you take any vector in Rm, and probably you want it not to be in the kernel of this covariance matrix. And we define the moment generating function, which I use the Blackboard M letter, and I also put the subscripts A and L which define the random field, it is really just the moment generating function. As follows. And what we're interested in, or the RSD theory, is essentially going to give you some very nice monotonicity properties of this moment generating function as you vary either A or L. So before I present these monotonicity statements, let me just give some examples. So how to get the ZGF that was mentioned above? What would it be in this language? Take your finite lattice, let's say minus L until L. It doesn't, by the way, have this theory, this monotonicity theory is not special to 2 dimensions. It can be in any dimension, really. So you take this as your initial graph, as the set of points on which the ZGF field is defined. And then the dimension M is going to be the size of this lattice, which in this case would be 2L plus 1 to the power D. And now these functions from lambda to z, which is the configuration space of the ZGF, is really just isomorphic to Zm, of course. And that is our lattice. That is the lattice that we take. So in this case, really just the identity matrix. As a covariance matrix, just take minus lambda times the discrete Laplacian on capital lambda, which we know is positive if we pick the correct normalization. Just to make it more explicit. So you see that you can exhibit the ZGF as one choice of such a lattice theory. Another possible choice is the Coulomb gas. The Coulomb gas, to remind you, has the same configuration space. There might be some fine print about whether you are in the kernel of the Laplacian or not. But anyway, you would really take the same lattice here. However, now the covariance matrix would be something slightly different. It could be something like this. So such a choice would give you the Coulomb gas, and that's also a valid possibility to use this theory to understand monotonicity properties. Yet another choice, which is not, it wouldn't be honest to say that this is a lattice theory, but you could say it's a disordered lattice theory, or and with a nil disorder, is the ZBF, which is even less standard than the ZGF. It's the Z-valued Bessel field. So we've been talking about Villain model and the ZGF, and they are dual of each other. And the ZBF, or the Z-valued Bessel field, is the dual of the XY model, which is also O2 symmetric. We preferred to speak mainly about Villain model, but I just mentioned that there is this dual of XY model, and that there is a way to understand it. Let me just write briefly what it is. So when you do this duality transformation, that you start from a XY model instead of a villain, then what you will find is the following partition function. So really, you find something rather similar where this Gaussian weight that was before is replaced by the modified Bessel function, which is why we call it, or at least I call it, Bessel field of order nx minus ny. This is an even function of this argument, so it doesn't matter if it's this or minus that. And this is really just the Fourier series of the xy Gibbs factor, which is e to the beta cosine of the difference of the angles. So that's why you get the this particular interaction. And one way to understand it as a annealed disordered lattice sphere is by the identity that this Bessel, modified Bessel function can be written as the following integral. So there is some probability measure for any beta. There is a probability measure mu of beta on 0 to infinity, where you can write it as an integral over Gaussian factors, and so that would be one way. It would eventually result in this covariance matrix that is disordered, this annealed disordered, but well, that is one way to think about it. I'll not speak more about this ZBF, this Z-valued Bessel field, and for now, I just continue with this RST lattice theory. So what is it at all? What are these monotonicity theorems? All right. So they really all stem from a basic lemma. And for the next few statements, I really just summarize the paper of Regev and Stevens-Davidovich, which is remarkably beautiful. And in order to convey what we do, I need to explain a bit what is this RST theory, which, at least to my knowledge, and has not appeared before in the context of spin or height functions. So first is the remark that the moment generating function with a vector u times the same thing with a vector v, so two different vectors, is upper bounded by the square root of moment generating function of the same theory with the vectors u plus v times the moment generating function with the vectors u minus v. All of these square roots. If our random field psi were not restricted to a lattice, if it could take values in Rm, then this would just be an equality. So for the GFF, this statement is an equality. The main ingredient in the RST theory is the observation that for lattice theories, this is an upper bound. And out of this, they can make really beautiful things. So the first thing that they observe is that if you have the following structure of sublattice, namely you have two lattices M and L, and one is a subset of the other. A is a fixed covariance matrix, then you see that the moment generating function of the theory that is associated with the sublattice is actually smaller than that of the theory of the full lattice. V is also fixed. So we are only changing the lattice here. We're only changing the lattice here, and taking the smaller lattice will give you a smaller moment generating function. That stupid example is just that if you double the lattice constant by 2, then obviously we'll get a sublattice, and the moment generating function of the doubled theory will be smaller. And then out of this,
this lemma and theorem is about Gaussian fields or non-Gaussian.
It's about this random field psi that is associated with the two choices, A, the covariance matrix, and L, the lattice. So in particular, I would not call it a GFF. It's a lattice Gaussian.
Thank you.
Sure. By the way, please disturb me as much as you can because these Zoom talks can be lonely. So, okay, so next thing that they show, and this sublattice monotonicity we use crucially. So this will play a major role in what I'm about to say. Something that we don't actually use, but we find very interesting, is the following theorem that also appears in the RSD paper. Namely, if you have two sublattices, and L, which are both sublattices of L, then you have the relation of the partition functions as follows. So you see that the partition function associated with sublattice n times that with m is smaller than the full partition function L times the partition function of the intersection. And this can lead to, honestly, a new correlation inequalities. For example, for the ZGF, you can apply it in order to find the following. If you ask about the correlation of the event that nx and ny are equal, intersection with the event that nu is equal to nv, so you have these four sites and you ask whether the two events are correlated, you find that it's bounded from below by the product of probabilities. So we at least were not aware of how to prove this otherwise. Yeah. All right. A second monotonicity result that is also used in the sequel is the following statement. It's telling you that if you have two covariance matrices A and B, both of which are positive, and they have this relation of operators at the level of operators or matrices, then the moment generating function that is associated with F is actually smaller than that is associated with B. So,
do you mean that the quadratic form of A is bigger than the quadratic form of B?
Yes.
Okay.
I mean, you can think about it spectrally or in terms of the eigenvalues of all the eigenvalues. Or
yeah. Thank you.
This is also a crucial statement for us, and it immediately implies that the mapping that takes the coupling constant to the ZGF fluctuations is a monotone decreasing. So this is elementary, but still let me just explain why. So we'll take as your vector V to be the difference of the Kronecker deltas, which is in the complement of the kernel of the Laplacian. And then obviously the second moment is related to the moment generating function like so.
May I also ask one question? Is it necessary that those moments exist? Is this conditioned by the first lecture? Is there any limitation here?
This is not really a question that we need to worry about because we are always defining our theory in finite volume, and we then take the limit, for example, after having calculated the second moment, and it is actually precisely this monotonicity that shows you that you can take the limit and that it will exist. Of course, you know, you need that this covariance matrix is positive, which tells you that the sum over the lattice is going to converge.
Okay, thanks.
Sure. So this relation between the MGF and the second moment tells you that monotonicity of the MGF will imply that of the second moment. And so we would conclude this corollary based on the observation that this is operator monotone. All right. So now that I feel like I presented most of the RSD theory, let me show you what we do with it. So what I want to convince you is again that the second moment, so what we call the fluctuations of nx minus ny for any two sides x and y of the ZGF on some any double periodic planar graph. But to be concrete, let me take Z2 with coupling constant lambda are bounded from below by those of some other graph with degree 3 that has coupling constant 4 lambda. And so if you make sure that the right-hand side is delocalized and the left-hand side is delocalized as well. And so how do we do this? We proceed in several steps. And so the first step that we do is the following. We just plug in, it's an identity to take your field theory that is defined on any point on these vertices and add to it an auxiliary degree of freedom on the mid edges, like so. These are the red dots that I'm adding. The black dots are places where the field takes values in Z because it's a ZGF. The red dots, however, initially at least take values in the real line. And the way to introduce this is really just an identity, is to use the following relation. So once you plug this relation into every single Gibbs factor of every edge in your theory, then you get this new picture that I just drew here that has this mixed Z and R valued Gaussian field. And what's crucial about it, let me use this, is that what was lambda before, or 1/2 lambda, now turned into lambda. So the coupling constant has doubled by introducing this additional degree of freedom, real valued degree of freedom. So that's the first step. The second step that we do is we want to actually constrain these red dots to take integer values instead of real values. If you think about it, what we're doing is we're constraining the field more, so it stands to reason that it should fluctuate less. And so fluctuations should go down when you do this, but still how to understand it. So one way to understand it is that the MGF of the mixed theory that has both Z on the vertices and R on the edges can be thought as the epsilon limit of the theory that has Z on the vertices and epsilon Z on the edges. And so if we take the limit along appropriate subsequences, for example, such choices, then you can see that as you take the limit epsilon going to 0, the fluctuations only go up, so that the fluctuations or the moment generating function associated with the left-hand side here is actually the largest in this sequence. And so we find this result and this is really by sublattice monotonicity that I mentioned before. Right, because 2 epsilon Z E is a sublattice of epsilon Z E. So now we have a new theory that has Z-value degrees of freedom on both the vertices and the edges. However, the coupling constant has been shifted from lambda to twice lambda. And I remarked that this is, I think, relatively simple, but still non-trivial result, because if you just went in a plain way and introduced these additional degrees of freedom on the mid edges without changing the coupling constant, then actually it's very easy to show that fluctuations go up, right? You allow the field to be more elastic, of course it's going to fluctuate more. So it's only by introducing the mid edges and simultaneously changing the coupling constant that we're allowed to say this result. All right, so that was the second step. And now the third step, which is the crucial one, is the following. So we take a look at just one vertex, right? We have the initial degree of freedom here, and then we had the 2 additional ones that were on the mid edges. There are 2 other ones, but let me not draw them in the picture. And what we do is we restrict to a sublattice where the 2 red degrees of freedom take the same value. And so you get the following new picture. And in this new picture, now this coupling constant is 4 lambda, because you have the two interaction terms in between the black and the red. And otherwise, it was twice lambda that it was before. And so, again, because of sublattice monotonicity, we see that this new theory, and this is really now a new graph, this G tilde that is cubic, right? We see that it has degree 3. We have the result that the moment generating functions only went down in all of these steps. And finally, if you want to have that the coupling constant is 4 lambda everywhere, then you just use the covariance monotonicity that I mentioned before. And so that's how you find this result here, which in conclusion extends the elementary proof of Lomer's also in elementary way, so now that it can be applied to more general graphs. All right. So that much for the ZGF delocalization. Now, just as much as time permits, let me say a few words about...
May I ask a question?
Please.
Yes, so I got lost on how you could condition the two red points to be equal in step 3 and not lose any, I mean...
Well, I'm looking at the sublattice in configuration space where these two red points take the same value.
Ah, okay.
This is a sublattice of the initial one.
Okay, this I haven't seen. Yes.
And yeah, and because it is a sublattice, then I can apply the monotonicity with respect to it.
Cool. Thank you.
Welcome.
Okay, so it's my turn not to understand. So I was understanding from far away, and now that it's getting precise, I don't. What's is it possible to re-explain once more how we take care of making two red points equal? I'm sorry for missing the argument.
So I'm saying that I have my lattice of configuration space, which is really the set of functions and I'm saying that this is a superlattice of the set of functions where these two red sites take same value. And because of this, I can use, I guess, this theorem.
Okay, makes sense. Yeah, I believe I was, I don't know if Avelio's concern was similar or not, but in my case, I kind of forgot meanwhile that the red points were integer now, that we removed the continuous part. So, okay. Thank you. Sorry for interrupting.
No. As I said, I welcome all the comments and interaction. All right. So not a lot of time, but let me at least start. So the second point that sort of on parallel track, I'll just say as many words as I have time for. Is this implication that says that ZGF delocalization implies the Villain BKT. And why this is so was really presented through a crucial, as Michael was saying, a new relationship. It's not exact, it's a lower bound, but still between the 2-point function of the Villain model one way to write it is as the cosine of the difference of the angles. So before Michael was writing it as a sigma, inner product, where sigma is this two-component unit vector in R2. Of course, it's equivalent to the cosine of the difference of the angles. And the new inequality is that this is bounded from below by the probability that there is a path of these level lines at any level k. So in principle, in order to start explaining this, you look at your field, which takes different values on each plaquette. And by the way, let me be a bit more precise. So this is with coupling constant 1/beta. This is for the ZGF. This is on the graph G, and this is on the graph G star. All right, so on the graph G star, you have your plaquettes, and you identify these points where n is greater than k, k being any half integer value on one side, and n is smaller than k on another side, and you draw a line on every such edge that separates two such faces. So for example, if you pick k equal to 1/2, and here you have n equal to 6 and n equal to 0 here, then you would add such a red line. And like that, you can construct many edges, and each edge would maybe yes or maybe not carry such a k line, and then you can connect them together. And they will necessarily form closed loops because n is such a function, and we give them the orientation that on the left of it, you'll have the larger value, on the right of it, you'll have the smaller value. So they will continue to loops like this. And we can also make sure that they don't intersect. And the way to do it is for example, if you have such a possible intersection point, so you would like to maybe add your lines like this, but you don't know how to resolve the conflict, then you just pick once and for all that you'll always resolve it with this right-hand rule. And if you make this choice, then you'll always be able to avoid intersections. Like that, you get a system of loops for each value of k, which is half integer. You get a system of loops, and they are not intersecting. At each edge, there will be a maximum number of loops that pass. You get exactly nx minus ny number of such k loops allowed to pass. And what we are saying is that the two-point function of the villain is bounded from below by the probability that there is such a path. It's not just any path. There's some restrictions. So fix any value of k, and it will be true for that value of k. And moreover, we saw that this villain two-point function was really equal, not bounded from below, but really equal to this ZGF insertion of a defect line. This did appear in Michael's lecture. So if you have these 2 points x and y, and you pick any path in between them, for example, this L-shaped path, then what this right-hand side means is you take the ratio of partition functions in the downstairs denominator, you don't modify it at all, but In upstairs, you ask that it jumps by 1 across this contour. The contour is still arbitrary, but fixed. It doesn't change with the realization. And this is what this observable T stands for. Really, it is just the correction to the energy. That's what this T would stand for. So the event that there is a K level from X to Y also depends on this choice of gamma, and it is asked that this K level doesn't intersect the deterministic path gamma. So this path we call KXY, this we call gamma YX. And so how do we actually show this inequality? So you start with the exact relation, which is really just this one. And because this T is a positive quantity, then you're allowed to put in the characteristic function for the event A for any choice of K for no cost at all, right? I mean, you get a lower bound, but you're allowed to do this. And now what I would like to show is that under this characteristic function, this expectation value is actually greater than 1. So actually what I find is really just the probability of this event. And so in the interest of time, I don't show you all the details, but let me just show you the main idea or the gimmick here. So you have a deterministic line where the field is asked to make a jump by +1. And you have a stochastic line where there was some difference, and because that's what the event A asks for. And you know what it says. It says that N is greater than K over here and smaller than K over here. And there is quite a bit of things to check, some fine print to make sure of, but under the knowledge that really you have this stochastic line, the question is putting on this deterministic defect, is it a good effect or a bad effect? And our statement is it can only help you. And that's why really this expectation, this which you can write as a conditional expectation, is really greater than 1. So why that? So for a change of variables, which you do only in this region, you change from N to N minus 1, you can eliminate the deterministic defect line. So you get nothing happening here. However, what you change now is the boundary condition on the blue line, so that instead of having the stress N smaller than K here and N larger than K, you only get N larger than K minus 1. And so there is actually less stress. And if what the partition function cares about is elastic energy, then you've reduced it. So there is a statement here that the partition function with some boundary condition, and these boundary conditions would be to make sure that there's a certain difference between this line and that line. This I denote by F. This partition function that is somewhat lowered on just the brown line is actually larger than the partition function with the boundary conditions that were unaltered. And that's because you just lower the gradient that has to be there anyway. And so, okay, this is for a conditioned partition function that has these specific boundary conditions, and we have a way to relate it to this quantity over here. So this statement that lowering the gradients can only make the partition function better, this we call the stiffness modulus. And while it's very natural, it still deserves a proof, and it is true for the ZGF. So that I would say is one of the main ingredients in this lower bound. So I think I should probably stop speaking now. So thank you very much for your attention. It was a pleasure.
Well, thank you. So, applause.
Thank you very much.
And yeah, so if there are any questions, please feel free to ask.
Sorry, but Fröhlich and Spencer studied XY model, yes? But your result also is applied to XY model, or not?
So Fröhlich-Spencer is a very robust result because it deals with both XY and Villain, and they also independently of that, but using the same machinery, also prove ZGF delocalization. So you could say Fröhlich and Spencer deal with everything. Our result is mainly concerned with ZGF and Villain. We also have some things to say about the dual of the XY. And I also mentioned the work of Liss and Van Engelburg that deals with XY.
Mm-hmm. Thank you.
Welcome.
Maybe following this question, are the results also possible to extend to any periodic graphs? You have double periodic, right?
Doubly periodic, yes. This surgery that I described should work for any doubly periodic planar graph to reduce it to a degree-free graph.
But is it possible then for any periodic in general graph?
I mean, I guess you can do the surgery, but you know, the phenomenon of ZGF delocalization is very special to 2 dimensions. It's, you know, not true in 3 dimensions. So okay. I wouldn't know why to do it there.
No, if I may, if you just assume single periodicity, you are not making, for example, under translations in the X direction, you're leaving room for all kinds of strange behavior in the Y direction. For example, the couplings may increase in an irregular manner or decrease. I have to stop and think. Is that what you meant?
Yes, yeah, it is answered now.
Yeah, so you can in effect change the dimensionality of the model this way. You can turn it into 1-dimensional. No, sorry, or you can tie it down. In other words, you want some degree of homogeneity, strict or not, but it should be roughly homogeneous. And if it's just translation invariant in 1 direction, you have to stop and think what happens in the other. And
okay.
I have to stop and think, but I'm not sure that this would be valid.
So in general, this is only a question of dimensions, right? In this case.
In essence, yes. And you require a certain degree of homogeneity.
Okay, thanks.
Are there other questions? I have maybe a couple. So one is, yeah, so planarity is important, but I was wondering if, I mean, okay, for example, if we work in a tessellation in hyperbolic plane, do we, I mean, in one sense, it's planar, so it's 2-dimensional, but in terms of volume growth, it's infinite dimensional. So do any of the 4 authors have any opinion about what should happen in this kind of stuff? I'm not claiming the question is interesting, but just asking.
You want to take it?
In the hyperbolic plane, if you take the real valued Gaussian free field, you can easily check the Laplacian, and you can easily understand the behavior, and you will find that it's localized. If you put 0 boundary conditions, then the field will be flat in the center of your domain. And you, in general, have that the integer valued Gaussian free field is less fluctuative than the real valued one. There is a Gaussian domination. So it will also be flat. And you don't expect any of this Kosterlitz-Dawes type mechanism to occur.
Yeah, Pullman's way of thinking about hyperbolic plane is that to some extent it's similar to a tree, which also has exponential growth.
Yes, putting 0 boundary conditions.
Tree is even more localized than 3 dimensions. So there is no phase transition there.
Yeah, which makes sense. And I had a second question, which is not strictly speaking mathematical, but you mentioned that this theory of monotonicity wasn't used before in this part of mathematics, like this part of statistical physics and so on. So how did you come to know about it? Like, how did it travel from computer science back to us?
I mean, Ron is really...
There's one answer, Ron Peled.
Yes.
We found it on Google.
Okay. Yes. Okay.
Good luck. Let me add a comment that what this theory, which is absolutely beautiful, permits you to do is sort of equivalent to what in a pure spin language perhaps is accomplished by Ginibri inequalities. Sort of similar flavor to some extent.
Not very close again.
Okay. Thanks a lot. Okay, so can I have a second round of applause for both speakers of this session?